Since the early 90s, we've had a lot of manufacturers that have jumped on to the line array solution. They've provided products that really are a very good solution for touring sound. Unfortunately, a lot of manufacturers and customers try to force the line array solution into fixed installation. And invariably, in most of the venues, auditorium, churches, even stadiums and arenas, the vertical coverage angle that is needed is almost always more than 50 degrees, and it's typically 70 or 80 degrees of vertical coverage. The problem is that to do it with a conventional line array box, you need many modules that are fixed to a given angle. 10 degrees is quite common. And you end up with an array that ends up taking on some sort of J shape, because the challenge is always, how do you cover the seats that are closest to the line array with something that's really designed to throw sounds a long way away? And the sort of compromise that people started using is allowing the boxes to be splayed or spaced apart between boxes. And as soon as you start doing that, a lot of the benefits that you can get from a line array disappear. Having to use DSP processing and all sorts of other tricks to sort of patch up and try to make the best out of a bad situation. So that was really the background to this new range of speaker systems, is trying to come up with a from scratch system topology that would allow us to take the best attributes of a line array system, but add to that the ability to achieve uniform sound pressure level front to back, uniform and consistent tonal balance across the seating area, and good coverage. We really want to deliver a custom solution without using a custom product. And that's really the whole essence and innovation, if you like, in this product, is that by having individual components that can be put together in a flexible manner, what we have is 15 different building blocks. And those building blocks differ in coverage angle from 55 horizontal and 5 degrees vertical, all the way to a much lower Q or wider directivity product of 120 degrees horizontal by 60 degrees with 15 different stopping points on the way. But the real power comes from what happens when you actually build an array and you put a system together. You have a fixed location to mount the loudspeaker system, and you have projected onto the floor a rectangle or a trapezoidal shape that you have to cover with uniform sound. Those angles are different at different parts of the array. You're going to want a high Q or very narrow horizontal angle that's throwing the furthest, and then as you come down and you add more boxes, those angles are going to open up till you get down to the bottom of the array and you have what we call a short throw box, where you may be employing a 120 degree horizontal box. If you think about it, the number of permutations, arrays that we can construct out of these 15 different modules, you would begin to understand the power of just how many permutations we can create, which obviously gives us a much better chance of being able to paint the seating plan with uniform tonal balance and uniform sound pressure level. We hit upon the innovative approach of breaking the diffraction slot, which is at the beginning of the waveguide that comes out and delivers the sound to the audience. We took that slot and we broke it down into segments. Rather than having a single compression driver that feeds a 12-inch or 15-inch slot, what we have is we have 6 individual devices that build up and feed that slot. The consequence of that is that the depth is much reduced. But also in the physical way we have been able to put the devices together, by having individual segments, it gives us the ability to actually create anything from a straight line of segments to something that has a very deep curvature. The physical dimension is very crucial. We have particularly chosen a dimension that is around 2¼ inches tall. That dimension happens to coincide with the first interference mode you would have if you put two sources next to each other. At 15 kilohertz, you just begin to start to get interference effects in the far field. So by limiting the height of those individual elements, we're able to make sure that not only is there no interference within a given module that is made up of 6 diffraction slots and 6 compression drivers, but also that same performance continues between modules, because we've also, in the physical makeup of the modules, we've ensured that that diffraction slot continues almost uninterrupted right the way down the complete array. In doing so, we've ensured that that same continuous, smooth, interrupted performance is achieved into the far field. So that really is a key part of the design. We have designed new components from scratch that have the ability to cover a more extended bandwidth. We're looking for a device that goes down to 500 hertz. It gives us the ability to have substantial control below a kilohertz, which is almost unheard of with this type of product. You don't have directivity differences that are in the middle of the crucial vocal range too. We wanted the basic module to be a full range module, so that if you use it as a single device, that it will sound impressive on full-range materials. So we're looking for a relatively low frequency performance. And with a two-way system, that means that the low-frequency device also has to cover quite an extended bandwidth. The 10-inch woofer that's used for the lower frequency section is covering 60 hertz to 500 hertz. That is actually still quite a large bandwidth, particularly once you get above 250 hertz. It's important that our customers have the ability to both combine subwoofers with an array in a hung system, or alternatively to ground stack or hide the subwoofers away, which is very often the case. We've designed the bandwidth to be very solid down to 40 hertz and to cover up to 200 hertz. And we have tailored the waveguide and the port design in the subwoofer to maximize the acoustic energy we can generate within that bandwidth with the lowest distortion.